So you are in which year? Means you are from which department or
MSc first.
MSc second year?
MSc first.
First year.
Yeah,
Okay.
chemistry department.
From where? Which institute?
CUT, Central University of Jammu.
Central University of Jammu. So as it is 6, we can start, and so let me share my screen. Let me know if my screen is visible right now. I guess it is. And is my screen visible to you?
Yes, sir.
Okay. So I can understand only you are there. So if you want to leave, you can tell me. And anyway, I have to record this session. And so now let me welcome you to the live discussion sessions of molecular spectroscopy of physical chemist perspective. Actually, this session is run by Professor Aninda Datta. He is actually my supervisor at IIT Bombay, my PhD supervisor. He took this course long back in a classroom fashion. I think we have already seen a few weeks lecture. And so what we will try to do in this 2 hour time, that we will try to get the solutions of the weekly assignments from the previous week. Suppose you week 1 and week 2 are due on, I think, 8th February, that is tomorrow. So we'll discuss those problem in the next week, because they will be graded, right? So today we will discuss only the week 0 assignment. Basically, I will ask you to give me the answer. If you can't, or I will give you hint, or anyway we will solve it interactively. And the second part will be, we will clear some of the doubt if you have any from the lectures. Lecture by lecture, I will tell something. I will try to add something if that is not been done in the class. And all this session will be recorded and available in YouTube, as you know. And the material discussed will be given you in a Google Drive link, and that will be shared by the NPTEL team. Okay. So to start with, for this course, which is most important, is that electromagnetic spectrum. I hope you know this thing, right? And I have taken this from wiki page, so the artist is Ade Stewart, so I am giving the proper reference. So as you know, that this is an electromagnetic spectrum, where the here is lower frequency means low energy, and it will go up to the higher energy, that is here gamma ray. I think you know this, right? You can see
Yes,
my
sir.
writing. Is it visible, or should I write it little bit in a
Sorry, can you repeat that?
so can you see my writing, or should I write it bigger font?
No, no, I can see it.
Okay, okay. So as you can know that from electromagnetic spectrum, this is our visible range. This is around 400 nanometer actually, or 350 to 400 nanometer, to actually the range went up to 750 or 700 nanometer, or 800, you can see. Oh, actually I have written a wrong thing. Actually this side should be 800. As you can see, this is the red part, right? 750, and this is actually 350 to 400. And this is high, and the gamma ray have the higher energy, and the radio waves have longer wavelength and less energy. So this is just to begin with. We will deal with all this kind of microwaves, infrared waves, in various kind of spectroscopy is going to deal with. So before going to the weekly assignment, I will ask you a few basic questions. It will not be difficult, I guess. And from this electromagnetic spectrum and molecular very basics of molecular spectroscopy, I hope we will do this fine. So can you tell me the first, what can be the answer to the first question, that the different types of energy associated with the molecule are, and the options is electronic energy, vibrational energy, rotational energy, D, all of the mentioned. So what do you think, what will be the answer?
All of the above mentioned.
All of the above, right? Yeah, you are correct. Actually, the thing is that in case of any molecules, we'll see that there is some. Let me show you the energy diagram. So you know Jablonski diagram. Do you know
Sorry?
Jablonski diagram? Jablonski
No, sir.
diagram. Actually, Jablonski is a scientist, and do you know what is fluorescence or absorbance or phosphorescence? This kind of term have you came across?
Yes, sir.
Yeah, so there is a to understand the basics of fluorescence, actually you need to understand the Jablonski diagram. The Jablonski diagram is consist of electronic states. Okay, so suppose these are electronic states with E1, sorry, E2. This is the first excited electronic state, and E1 is ground state, ground electronic state, you can say. You know this, right? You know, I hope you know this. So now these electronic states are actually consist of few vibronic states, and those vibronic states are like this. And the energy, if I give you the scale, it is something like that. Energy, ground state energy is less, as you know, and these are the things what I am drawing right now. Overall, this is an electronic states, and they consist of different vibronic states. Okay, these are called vibrational energies are there, and these vibronic state, each of these vibronic states, there are rotational energy state. Okay, so from this diagram you can remember that thing, that the electronic states, these are electronic, vibronic, and rotational energies are associated with this. So I will come to this question in a third question. Okay, so the second question is that during the motion of any molecule, if the center of the gravity of the molecule changes, the molecule possesses A, electronic energy, B, rotational energy, C, translational energy, and D, vibrational energy. What do you think? Which one is the correct answer? During the motion, if the center of the gravity of the molecule changes, then what does a molecule process? Obviously, it will process electronic energy, rotational, and vibrational energy. Oh, so I gave you the answer. So actually, the answer will be translational energy. Okay. So if the center of gravity is getting changed, so that will be means it has some translational energy. Now, can you tell me which? So we already know there are four for this study. What I am discussing right now. So we understand there are four kind of energies are there. One is electronic energy, second is vibrational energy, C is rotational energy, and D is translational energy. From this, can you tell me what will be the correct order of the different types of energies are? Which one? A, B, C, or D? You take your time and tell me. Avantika, can you hear me?
Yes, sir.
No.
Just a minute.
Yeah, sure. Take your time. Sorry.
So first,
The first one. That means E electronic is greater than E vibrational, then E rotational, and then E translational. Yes, you are correct. So, as I told you that if the molecule doesn't, if there is no motion, then these energies will be there, electronic, vibrational, rotational, but the translation is getting added when it will have some motion, and actually it has a very low value than the others. And from this diagram also you can understand, right? The electronic energy has the higher energy, and then they consist of some of the vibronic states, and there are some rotational energy in between. Okay, now with this basic understanding, I will go to the week 0 question, which will not be graded actually. So okay, so and then in the next week we will discuss week 1 assignment. So to start with, can you tell me from the first question, the first question, for the following molecule given, the symmetry elements that are not present is or are What do you think? Which one is not present? Point of inversion, so C2 axis of symmetry, C4 axis of symmetry, or mirror plane? Which one is not there? Anyone can answer. I think there are some few participants other than Avantika is also there. So this is just an introductory session where we are discussing the week 0 assignment, and then we'll go to the doubt clearing session where I'll lecture by lecture I will try to cover the thing, and you can tell me if you have any specific doubt from the week 1.
Is it point of inversion?
Point of inversion, you are correct. Point of inversion is not here. And what can be other? What do you think? Is there any C2 axis of symmetry?
Yes, that is also not there.
Why do you think so? I think there is one C2 axis of symmetry. I will show you.
Okay.
So actually the C2 axis of symmetry I think is along this line. If you see, if I rotate it like C2 means the 90 degree, right? So C2 is 180 or 90, 180 degree. So what will happen? So this thing will go up and this thing will come here, and it will be like this, right? So I think C2 is there. Do you get my point? Suppose this is, so for now I am writing it x1 and x2, they are same. What I am saying, after C2 what it will look like, I am drawing a smaller.
Yes, okay. Yes, yes. C2 is there.
C2 is there, right? Yes. What about C4? It's C4 there? C4 means 90 degree rotation, right?
C4 is not there.
C4 is not there, yeah. So it is also an correct, means here the correct option that is not present. What about a mirror plane? So what does a mirror plane do? Mirror plane, suppose if there is a mirror plane about the molecular plane, then what would happen, that suppose x2 will come here and x1 would have gone down. Or suppose there have been a mirror plane like the perpendicular to the molecular plane, suppose this is the case, then x2 could have gone here, right, and x1 would have come here. I hope the thing is clear what I am trying to say. So I think you can see the mirror plane is also not there. So I think you will be confused that why we are talking about symmetry here in a molecular spectroscopy course. Actually you will see that Professor Datta I think will be talking about this symmetry. He will discuss the symmetry part in details. Actually the symmetry part will be required. So just a basic questions from the symmetry are being given in the week 0, and I think it will be taught after week 4 or week 5 it will be discussed. So whatever the required part from the symmetry will be required, that will be taught. So don't worry about that. And so I think this question 1 is being cleared, right? That these 3 things are not present. So can I go to the next question, that the second one? Okay. So a chiral molecule. What is a chiral molecule? Can anyone tell me what is a chiral molecule? So the chiral molecule will be where the 4 parts can be different. Actually we learned it very earlier, but the actual definition would be that it will have a non-superimposable mirror image, right? The mirror image cannot be superimposable, then we can call a molecule chiral. So from the first option, from the definition itself, you can see that a chiral molecule will not have superimposable mirror image. So this is not a correct option to choose. Okay, so the first option goes up. What do you think? Does it have center of symmetry, or it lacks a center of symmetry?
It lacks center of symmetry.
Yeah, you are correct. So it will not have a center of symmetry. And what about, does it have a alternating axis of symmetry? That is an S. I hope you know. SN. is an alternating axis, and the principal axis or simple axis I think is denoted by the C of n, what we have done here, right? S n is we will perform some C n, and then we will perform a mirror, will have a mirror symmetry, will apply mirror symmetry operation perpendicular to that of the Cn of the principal axis. So then it will be known as alternating axis of rotational Sn. So so what do you think? Does it have a alternating axis of symmetry, or it don't? Any chiral molecule. I hope so to get me clear, I will. Yeah.
It may be there.
It may be there. What do you think about simple axis of symmetry?
Yes, it will lack a simple axis of symmetry.
Actually, no. So let me show you actually a chiral molecule. Let me keep this thing. I will take a help of Google, and I will show you here. Can you see my screen? Do I have it? Yeah. So can you see this molecule? A cobalt complex.
Yes.
Yeah. So this is actually a chiral enantiomer. But if you think that in between this, so I can't use the pen right now. Okay. So if you perform a C2 symmetry in between the two chlorine atoms, Cl, Co, Cl, in between, suppose in that angle, if you apply a C2, you will see that yes, it will have a Cn axis, or for this particular molecule it will be a C2 axis will be there. So I will not confuse you much here. So this will all be discussed, I guess, in the future lectures. So I will not be taking too much of time here. So, and to make it clear, it will lack a alternating axis of symmetry. It will lack. Okay. If it won't, then it will actually be a achiral molecule. So if I get some more time at the end, I will take an example and I will try to discuss. Okay?
So what is that answer? Necessarily lacks a simple axis of symmetry.
Yeah, necessarily lacks, and so it is not a correct answer. So necessarily doesn't lack an axis of symmetry. It can have one. So this is not a correct option to choose. So so we are choosing all the correct option for a chiral molecule. So a chiral molecule can have or may have, like the example I have shown you, may have a simple axis or the Cn as I have shown you, but it will lack an alternating axis of symmetry. So it will lack two things: one, centrosymmetry, and another thing is alternating axis of symmetry. So if I have some more time at the end, I will try to discuss one example from this. So but for now, let me go ahead to the question number 3. So the question number 3 says the property that is not necessarily required for a group. To be honest, this question actually I am not sure of. What do you think? So do you know what is a group in a group theory? Have you studied group theory and symmetry before? Let me start with that. So is symmetry?
No, we are currently we are studying it right now.
Okay. So actually the group is, suppose you have some symmetry elements. So there are kind of symmetry elements what I am discussing right now, that principal axis of symmetry, then an alternating axis of symmetry, or a mirror plane. So these are all signs of those symbols of those symmetry elements actually. And identity E is also an symmetry operation. So these kind of things actually can make a group. We will call it, suppose one molecule can show all of these symmetry elements or any of these symmetry elements, then they will be called a group. And when they will be called a group, when they will satisfy a few points. So let me tell you one by one. So they must have identity operation. Identity is nothing but, suppose let me take a molecule CH4 maybe. Okay, this is a simpler molecule. Let me take this CH4, tetrahedral shape, all this pentane atom are hydrogen. So see, so if I perform an symmetry operation or symmetry operation of E, then it means it will do nothing. Okay, let me name it H1, H2, H3 and H4 to understand. So it will do nothing. H2, H3 and H4. Okay, so they must have an identity E. So to form a group, they must have an identity E, and they should. So this is this will go away. So the property not necessarily required identity element. So this will, if I choose this one, it will be a wrong option. So necessarily it will have an identity element. So that is from the definition of a group it will come. And the other things are that whatever the symmetry operations are there in group, they should be show commutativity and associativity also. So associativity means, suppose there are, so let me call it by A, B and C. Suppose these are all symmetry operation, so they should all have associativity, right? A is B and A into B. I think this, what is associativity. So suppose A, B, C are all symmetry operations. Okay, so if I operate C first and then A into B, so it will give me the same result if I go perform B into C first and then A. So these are just an axioms I am talking to you about, and there are some other. So an inverse property, they should also have some inverse property. Inverse means what I am trying to say, suppose they have C of n as a group in a group, so the group should also contain Cn inverse, and Cn inverse can be anything. Cn inverse can be suppose how can I say, so these are actually all can be represented in a matrix form. So you know how to get the inverse of a matrix. So this is going to be another operation. Okay, another symmetry operation, what I am trying to say. Suppose what I am trying to say here, so if you have a symmetry operation in a group, then you should also have A inverse, which is a B symmetry operation. So these are A, B, these are all symmetry operations. Okay, so actually to come to the end, actually the closure property should also be there to call it a group. The closure property means if you have A symmetry operation, B symmetry operation, suppose this is your E is actually the identity, what I am trying to say. Suppose this forms your group, so it should be like that. If you have A cross B or A dot B, you should also get the same same molecule. Or suppose you are operating A into B. Actually A into B means you first operate B and then you operate A. So suppose you will get something here, so you will get the same thing if you operate A first and then B second. So this is called closure property. So you actually, these all are required, but the correct option I think is given closure. So I also don't know why they have choose this thing. I'll talk to the professor, and I hope he will discuss this in the class. Okay, so let me go to the next question. For the next question I will use a photo. I'll take this. I have taken this photo from the masterorganicchemistry.com. So I've given the reference there. So the question is actually for benzene. We have to select a few. What are the correct option we have to choose? So the options are, there are two sets of degenerate pi molecular orbitals. The second option is number of antibonding pi star molecular orbital is given to the number of pi is equal to the number of pi bonding molecular orbital. The highest energy antibonding pi star molecular orbital is antisymmetric with respect to C6, and the plane of the molecule is a mirror plane of symmetry for at least one pi molecular orbital. So is this question clear? Avantika, and what is the name of other student? I can't see actually your names if I am here in the presentation mode.
Subramaniam.
Okay. Hi, I am Orko. So Subramaniam, can you tell me which options are correct?
Normally, the pi star should be of a higher energy level than the pi.
Pi star, yeah, that is there. Pi star, these are all antibonding. So pi
Antibonding orbitals are at a higher energy than the bonding moleculars.
Okay, but there is no such option. So see, so for benzene the options are, there are two sets of degenerate pi orbitals. Is it correct here from this picture? What can you see?
Degeneration.
Degenerate means the energy will be same.
Yes.
So as you can see, the pi 2 and pi 3 these are bonding MOs, right? These, but they have the same energy, right? If you see the nodes number, from the number of nodes actually you can judge if the number of nodes, let me tell you number of nodes, if number of nodes is high in symmetry, this is very required. If the number of node is high, then the energy of that MO molecular orbital will also be high. So as you can see, for the pi 1 there are no nodes, right? You can see there are no nodes. So these are all p orbitals, right? For carbons 2p, I guess. So as you can see, there are no nodes. So they are all in same phase for the pi 1. But pi 2, as you can see, there is one node in the molecular plane. So it is something. How can I tell you? It is something. If you can see, if you go from here to there is a change in the phase, right? So there is one node along the perpendicular to the molecular plane. This is the molecular benzene. This is the molecular benzene molecular plane for the benzene. I guess you know this. This is the molecular plane and perpendicular to this. So there is a node. Actually, this is a nodal plane. You can think of something like this. Okay, and perpendicular to that of the plane, you can see there is a node, and here there is a node. If you can see, for pi 3 there is one node. So all pi 2 and pi 3, both of them have one nodes each. So they will have the same energy, means they are degenerate. And similarly, if you see for pi 4 and pi 5, there are two nodal planes each, to pi 4 star and pi 5 star. So eventually they have two nodes, so they will have higher energy than pi 2 and pi 3, right? Pi 4 and pi 5 will have higher energy, what you have said earlier, that antibonding will have higher energies. And if you can see that there are two nodes and both of them have two nodes, means they are also degenerate. So pi 4 star and pi 5 star are degenerate, and these two are also degenerate, right? So yes, the first option will be correct. There are two sets of degenerate pi molecular orbitals, not going to bonding or anti-bonding. So can you tell me if the second option is correct or not? number of antibonding molecular orbital, pi star molecular orbital is equal to the number of pi bonding molecular orbital. Is it correct? Avantika, Subramaniam, what do you think?
Yes, sir.
It will be correct, eh?
It is correct.
Yeah, all of them has three bonding and 3 antibonding. Yes, so it is also correct. What about the highest energy antibonding pi star molecular orbital that is antisymmetric with respect to C6? This is pi 6 star. This is the one what is for option 3, that if it is it has the highest energy antibonding molecular orbital, is it antisymmetric to C6? C6 means we will rotate. So this is the principal axis actually. This is the principal axis. If we rotate C6, C6 means 360 by 6 or 360 by n, 60 degree. Yeah. So what do you think? If we rotate 60 degree, if we rotate it, will it be symmetric? I mean, the symmetry will be retained or not? From the
It will be retained.
It will be retained. Why do you think so? Sorry. See, you have to think about these phases also. These are all p orbitals, right? So pi 6 star, if you can see here, this has a positive lobe. Suppose we are talking it positive. In further study, when you go deep into the symmetry, so that are actually not plus minus, they have different phases actually, and this has, suppose the node positive lobe is there. So do you think if I perform a C6 symmetry operation, will it overlap with each other, or will it be a symmetry operation?
It will be antisymmetric.
Antisymmetric. It will not be a symmetry operation. So the highest.
Sir, sorry, there was a power cut, so I was suddenly interrupted.
Sure. So
Can you tell me why you have chosen these two answers? There are two sets of degenerate pi.
Okay. So I will repeat that thing. So if you can see, so we are discussing about if now number of node is high, then the energy of that MO will be high. These are all MOs, right? Molecular orbitals. Pi 4, pi 5, pi 2, pi 3, pi 1 and pi 6. These are all molecular orbitals. And here is the actually the p orbitals are given for each carbons, and actually this will come from the Huckel MO theory. If you read further, go into the symmetry, and this will what look like. So if the number of node is high, then the energy will be high. So if you can see, for pi 2 and pi 3 there are only one nodal planes, but for pi 4 and pi 5 they have two nodes each. So eventually it is correct that this pi 4 and pi 5 have higher energy than pi 2 and pi 3. Okay, so that has been established, and you have also said that the antibonding will have higher energy than the bonding molecular orbital.
Yes.
And if you can see, now the number of nodes is same for pi 2 and pi 3, and they also lie in the same energy, so they are degenerate. Pi 2 and pi 3 are degenerate, and pi 4 star and pi 5 star are also degenerate. They have two nodal planes each. Okay, so the first option is correct because there are two sets of there are two sets of degenerate pi molecular orbitals. One set is pi 2 and pi 3, another set is pi 4 star and pi 5 star. So that is number one. And the second one is the number of antibonding pi star, or means the number of antibonding molecular orbital is equal to the number of bonding molecular orbital, pi bonding molecular orbital. If you can see, there are 3 bonding molecular orbitals and 3 antibonding pi molecular orbitals. So actually that is also correct. So right now we are discussing with Avantika told that the right answer, that the highest energy antibonding, that is the pi 6 star, that has the highest energy. Actually it will be antisymmetric with respect to C6 operation, symmetry operation, rotation. C6 means we will rotate it 60 degree around the principal axis, and if you can see, so if I perform a C6 operation, it will look like, I will show you how it will look like. So this is the molecular plane. Suppose I have already rotated it. so it will look like, so suppose this is 1 2 3 4 5 and 6. So how it will look, the 6 will come here, okay, the 6 will come here with a positive loop up, this is 6. And now, so this numbering actually doesn't really mean anything, just to show you right now that I have came from here to here, that's why I am writing it like that. Actually the number doesn't mean anything. And then the 1 will go here and 2 will go here and 3 will go here. This is 1 2 3 4 will look like 4 will go here, and in place of 6 5 will come, so this is 5. Can you see that if I operate a C6 operation from here to here, actually those will not be means this and these two structures, the pi 6 star and suppose pi 6 star after C6, actually they will not overlap with each other, or they are not symmetric. So that means it will, this pi 6 star, actually this antibonding molecular orbital is actually antisymmetric with respect to C6. Means the C6 we can't really C6 can't be a symmetry element to that pi 6 star molecular orbital. So actually this is actually a correct answer, that it is antisymmetric with respect to the C6 rotation. So what about the plane of the molecule is a mirror plane of symmetry for at least one of the pi molecular orbital. Means can you see, so there is one molecular orbital here, 2 are here, 5 and 6 molecular orbitals are here. Can you tell me if for any molecular orbital sigma, that is the mirror plane symmetry element, sometimes we call it element and sometimes we call it operation. So when we are performing something, suppose we are rotating 60 degree or C6, so then I am saying I am operating C6, or C6 is operation. But if after performing C6 it is a symmetric thing, so then I will call it that C6 is a symmetry element to that of that molecule or that of the M. Okay, so if I so the mirror plane is I showed you, so the actually this will not be a correct so actually for benzene, the plane of molecule is a mirror plane of symmetry for at least one pi molecular orbital, not a pi star. So what do you think? If so molecular plane is this one I told you, so is it a can a sigma be a element, say symmetry element for pi 1? Subramaniam or Avantika, can you tell me? So the if I perform a sigma, then the positive lobes will go down, right, and the negative lobe or the opposite lobe will come here. What do you think? Then will it be symmetric?
No.
No, right? So sigma is not a symmetry element for pi 1. What do you think about pi 2 and pi 3? Will it be symmetric if I perform a sigma along the molecular orbital, a molecular plane? Sorry.
For pi 2,
And
yes.
pi 3. So then the positive lobe will come here, all this place, and this positive will and the negative will come down then, but it won't be actually symmetric to that of the pi 2 that is already existed, right? So suppose this is what we
You mean the up will go to down, down will go to up?
yeah, then it will not be symmetric to the pi 2.
No, it's only a mirror reflection, no?
Yeah, so I am talking out on the molecular plane. Acha, let me show you what will happen after doing a sigma operation, or if I put a mirror plane there. Okay, on the molecular plane I'll show you what it will look like. Suppose this will sign will change. The positive lobe will go up and positive lobe will go up. So what do you think? These pi 2 and pi 2 after sigma are the same? Only after doing sigma. You can't rotate it. Means you can rotate it. Means after only doing sigma, are they same?
No.
No, right? So sigma is not really a sigma symmetry element for pi 2, and similarly for pi 3 you will also see this will go up. So actually sigma will not be a symmetry element for any of these molecular orbital, because their p orbital looks like this, right? One will be some positive lobe and negative lobe. I should not really say, I am saying this multiple times, these are actually not really defined as positive or negative. Actually they means that different sign is there or different phase is there, to be clear. So that is not really a plus minus thing what we have till now read in BSc level or in 12. Okay, so they are different phases, and that actually is covered, I think, in quantum chemistry lectures. So that is a issue of a different course, but let us focus here. So all our p orbitals are there. So because of that if you operate a sigma operation here, so every time you will get a different thing. So that is why sigma will not be this mirror plane symmetry is the sigma operation. So the charge is very low. Let me quickly add the charger. Sorry for the interruption. Very sorry. Wait. This. Give me 1 minute. Okay. Pen is also that. Can you still hear my audio and can see my screen? Can you still see my screen? Anyone?
Yes.
Okay, thank you for confirming. So what we are discussing there, for so sigma will not be a part or symmetry element to any of this pi MO. So this is actually not a correct option. Okay, for benzene all three will be correct, and the third is like that. So with that, this assignment 0 problem we have already discussed, and now what I am going to do is that we'll so we have 1 hour and 15 minutes left. So what I'm going to do, so we'll discuss the week 1 lectures, the topics which already have been covered, and I will try to clear some of your doubts, and we'll do it interactively, and topic by topic I will go. Suppose lecture 1 frequency domain thing was being studied, instrumentation was there. There have been some lecture about the resolution. So do you guys already seen week 1 lecture? Have you finished that?
Yes.
And now I guess the week 3 lecture is already being circulated. So have you watched all week 1 and week 2 both, or till now you have done only
week 2 not as yet.
Okay, good. So no problem, and I think tomorrow is the last day to submit the assignment.
Yes, but why is it that assignment 1 is also on 8th, assignment 2 is also on 8th?
Yeah, but that is not going to be true from the means that the assignment submission date will be different for week 3 and week 4, means it will be 1 week by 1 week, because the students are still getting enrolled. So the last enrollment date I think was 6th February, means the yesterday. So
Okay.
it has been given some opportunity to those students who are joining last, so that they can submit their assignments. So we'll discuss the lectures from week 1, and if you have some doubt, we'll discuss that, and we'll discuss week 1 assignment maybe on the next actually on the next week. So actually week 0 will not be graded, but week 1 and week 2 will be graded, so we can't really give you the solution or discuss the solution here, but we'll discuss some formula what can be used. If you have some doubt, you can always tell me. I will not give you the answers, but we can anyway discuss this. So I have all the blank sheet. Oh, we have another question, right? I missed that. I'm very sorry. I have another question. So have you solved this metric multiplication? This question number 5. So I missed that. So
Yes.
so what do you think? What will be the answer, and how to do that? So this is an 2 into 2 matrix, and this is a 2 into 1 matrix. Okay. So what do you think? What is the going to be a resultant? What is the going to be a this matrix? The product matrix will be what? How many rows will be there? How many columns will be there?
Two rows, two columns.
Actually no. So
No?
when you do yeah, I understand. I know. So I am coming. Actually, the answer what is being given, that is actually wrong in the assignment. Have you already submitted this and got it? Something like you have.
I did submit, but I don't remember what happened after that.
Okay. I think if it has already been the answer are being shown, then you will see the right answer is given something 2 into some of this 2 into 2 matrix, but that is actually not true. So let me give you a shortcut or a idea. So you can only multiply matrix when your 2 into 2, suppose your matrix m into n matrix. Okay, so you can multiply with only the matrix which will have n rows and some, suppose, p columns, and then only you can multiply. Means you can have two matrix to get you can get the product of that, and that will actually lead you to m into p, m cross p. So this part will not be there. So your resultant matrix will be m cross p. So for this case, you will get a 2 cross 1, or your product matrix will have 2 rows and 1 column. So you can understand that a result will be from this. Okay. So let me solve you how to do. Can anyone tell me how to do a metric multiplication? Or if there not much time is there, so let me do this. So what we will do here, so for the first, this part will be covered. So I already told it will be a 2 into 1, so let me take it much more region. So actually it will be 3 into 4, means the this element multiplied by 4 plus 2 into 6, means the first element from the suppose this matrix is A and this matrix is B, then the thing is that the matrix is going to be A, matrix element is going to be A11 is 3, okay, first row first column, and it will be multiplied by B first row first column, and A first row second column into B second row first column, and the below one will also be, suppose this will be A second row first column into B 1 the first one, and then this will be A second row first column into B 2 1. So from there, so you can check the matrix multiplication. Actually this is matrix operations. I think you have read it in, maybe if you had mathematics in 12, I guess already read matrix multiplication. Actually for symmetry purpose, matrix multiplication is actually a very important thing. So when the symmetry will be discussed, so that matrix will be required. Some idea of matrix will be required. One of such is matrix multiplication. Okay. So actually whatever the symmetry operations I was talking about, or symmetry elements, Cn, sigma, these things, actually they can be represented as a matrix element. Okay, matrix. And so I was talking to you associativity or the closure property, right, where Cn sigma should be sigma Cn. Means I am just taking one example. This is not true for all the molecules, just I am talking you about this here. So this here, to check these things or perform some operation, you will actually need matrix multiplication. Okay, so that is why this matrix multiplication will be required in symmetry, and those will be discussed. And you can take a you can see this thing online also. These are very easy. Subramaniam, Avantika, you already know this. Do you know these matrix things, matrix operations?
Yes, matrix. Yes, I studied, but very long back. So
Okay, I understand.
sure.
You can take a recapitulation. Quick recapitulation will help you. And so from here you can see what I have done already. They did this A11, B11, and A12 and 21 I have already done. And the second part will be 5 into 4 and plus 8 into 6. So the first step is I will check that what is my matrix is gonna be, that is 2 into 1 or 2 into 2. What, suppose I am multiplying a 3 into 3 matrix with a 3 into 3. Okay, so my product will be a 3 into 3 matrix. Okay, but suppose I am multiplying 3 into 3 with a 3 into 5. So I guess you will get 3 into 5 as your product. Here also we are doing 2 into 2 multiplying with 2 into 1. So that is why we are getting 2 into 1 matrix. Okay, it's not like that we are getting this part only as a back, but I hope that part is clear. So let me get this thing done. 3 into 4 is 12 plus 12, and here it is 20 plus 48, and we will see, you will get the C, option number C. But I have also checked this. If I have selected this answer, but it showed me wrong, but actually this is a right answer. So let me tell you that in some assignments the TA, so the live discussion, during live discussion I will be a TA, and some of the TAs are also checking the assignments before uploading. So they may have done some mistakes, and even if you are submitting the right answers and getting wrong results, suppose here if you select this, you have been shown that you have done it wrong, so your marks will be deducted. But don't worry, you can anytime post into the discussion forum of the group, and we'll recheck it, and I think the marks will be given. So you don't have to worry about that. You just let us know that there is some mistake. Okay, and even if you have some other doubts, you can post it in the discussion forum, and we'll try to get you back within 2 to 3 days or 1 to 2 days. We'll try to be very quick. Okay, so the answer is 24 and the 68. This is the correct answer for this matrix. So now we will actually go to the lecture by lecture. Week 1 and only week 1, 5 lectures are there. So we'll discuss that one by one. Okay. So are you with me till now? I think we have spent 1 hour, and another 1 hour will be there. So before starting, do anyone of you have any particular doubts from the lectures what is being taught by Professor Datta? Any particular doubts? I'll just check attendance. Okay, we have four participants. That's good. Kaustav and Shaptagiri is here. Okay. So I think you can hear me, right? What do you think about? Do you? So if no one is answering, then I'll guess there is no doubt, right? So I'll discuss topic by topic, and if you remember the topics, then anyway, if you remember your doubt, you can ask. Okay. So we'll start with week 1, lecture 1. I will try to be quick because these are already discussed in the videos, right? The first week, lecture 1, actually we have discussed frequency domain spectroscopy, right? So actually this was being taught, and where mainly two things are discussed, right? Absorption and emission spectroscopy, right? There are multiple kind of spectroscopy, but for these are two electronic spectroscopy. Okay, electronic spectroscopy. Okay, so from absorption, you already know there is something called Beer-Lambert law, and I think this has been derived, Beer-Lambert law, right? That A absorbance is logarithmic of I0 by IT, where I0 is the incident intensity of the incident light, and this is the intensity of the transmitted light. Okay. Sometimes there are some doubt, transmitted light, and this is the incident light. And that is actually will be equal to epsilon CL, and where you will see that epsilon is known as molar extinction coefficient, or some places it is Cn, or some places it is also known as molar absorptivity. So these are common terms, and their units are already being discussed, right? So this is concentration, this is the path length. And for emission, I think quantum yield was being discussed. I will come back to this quickly, but before that I will discuss about the instrumentation part of this. What sir already discussed, that the double beam spectrophotometer. And before doing this, I will just tell you this. I think you all know, right? This epsilon is an intrinsic property, right? Intrinsic property that of that molecule, and it is actually, we should write epsilon is a function of lambda, that is wavelength. Means at different wavelength, epsilon could be different. Okay. Suppose normally in frequency domain means the x-axis is in energy or frequency or wave number, whatever you can say, right? So frequency, or it can also be put in lambda also, right? The wavelength, and generally the unit is nanometer for this, and for wave number it is centimeter inverse. Actually, the spectra looks different in both the axes. If you convert from nu bar to lambda, it will be so lambda will increase here to here, and nu bar will be something like that. Okay, if you draw the spectra, so you don't have to think of this right now. We'll come back to later if you have some time. So suppose this is your absorption spectra. This is suppose your absorption. And absorption doesn't have any unit. Okay, suppose this is your absorption. You can also express this thing in terms of epsilon. So because if you already know the concentration and the path length, then in case of absorbance or OD, this is also known as OD, optical density. Okay, and so you can also express this y-axis in terms of epsilon, and then the unit will come, that is molar inverse centimeter inverse. Okay, and you will see the spectral nature will be same, but some part will be because it is epsilon is a by cl, right? So it will look something like this. So it will decrease, right? Decrease or increase. This is when you y-axis is a, or this is a epsilon. So you can see epsilon is actually your wavelength or frequency dependent thing. So I hope this part is clear, right? So what I was discussing about the double beam spectrophotometer. Actually, I will discuss another part what sir has not discussed here. This is the source, light source. So there will be some monochromator will be here, right? So by monochromator we will choose a particular wavelength, right? And then the sir has discussed there will be a beam splitter, 50-50 beam splitter, and 50% of that will go to your sample, and here will be a mirror, will be 100% reflective, and it is your solvent or reference. So why I am not writing solvent, because you can perform your perform the study in solid state also. Okay, but for solid state they use some different techniques that is not required for this course. Okay.
Sir, excuse me, I
Yes.
have some assignments to be submitted for by tomorrow in molecular spectroscopy.
Sure.
I have only 2 hours left with me.
Okay.
So kindly क्षमा कीजिए, I will take excuse.
Sure. And please don't call me sir. I am just a PhD student. So
Okay.
just
No
call me
problem.
on.
Thank you, sir. Thank you for the nice information
Thank
you shared with us.
you. Okay. Thank you for coming. I hope I will see you in the next lecture. Okay. So
Yes, sir.
Okay. So what I was discussing of the instrumentation, it will suppose I think in class it is being taught here is one detector and another detector will be here, but actually there is some problem in this setup if you measure the absorbance. I will just take this thing, draw this thing. Suppose this is a solvent in both the cases, and I will just add some lines here so that you understand there are some molecules. Actually these are all solute molecules which are already dissolved. Just to give you a perspective, I changed the color of that thing. And okay, so actually the problem what I was trying to say, actually not all the detectors, suppose you are buying detectors from the same company, but still the detector 1 and detector 2 will have different sensitivity actually. Okay, different sensitivity towards the intensity, that is also at different lambda. Okay, so actually we need to replace both the things with one detector, but that can also not be done easily from here. You can say that you can have a mirror here and then D2, but at the same time you can't measure I0 and IT, right? So what thing will be added, I will show you here. So suppose the source is being same, the monochromator is there. I will not write here much thing. Monochromator. Instead of beam splitter, we'll have a wheel kind of thing, one mirror system, which has 3 parts. One transparent, one mirror, 100% mirror, and one is actually opaque. Opaque means no light can pass through this part. So after that there will be your sample. I'll this, and here your another similar, but rest of the things are almost similar. Here is your reference, here is your sample. Sorry, is my writing is visible? If not, please let me know. Here is another mirror is there and another wheel is there before the detector. Here your detector will be there. Okay, detector will be there. Mostly it is a PMT detector. Mostly PMT detector means the photo multiplier tube. So another wheel is there, and which is the same thing, one transparent, one mirror, and one opaque. But the are you guys following me till now? Suppose this is wheel number 1 and this is wheel number 2. So I will need some response. So are you guys still following me? Can anyone respond?
Yes.
Okay, thank you, thank you.
Yes.
So these two wheels are actually synchronized. Okay, so synchronized such a way. Suppose for the first wheel it is transparent, so light will go through, right? So light will go through and it will hit on the sample, right? And it is synchronized in such a way that your second wheel there is a mirror part. So light will be reflected and it will go to the detector. So I'll repeat myself. So those two wheels are actually in a synchronized fashion. So when the first wheel will let the light go, means the transparent part will be there. The second wheel will be on the mirror side. So, and this will give me IT on the detector, okay? And another part will be like when the first wheel is in the mirror mode, so it will rotate very fast, okay? So when the mirror is in the first wheel is in the mirror mode, the second will be synchronized to transparent. So if this is in mirror mode, then the light will come here, fall on the mirror, and it will fall on the reference, okay? And as the transparent, it will be synchronized and the second will be transparent, so it will go to the detector. So this will give me I0, okay? But we also have to remember all these PMT detectors or whatever detector we are using, there are some thermal noise. Okay, the thermal noise means I will just check that if this session is being recorded or not. Yeah, so I just this is being recorded. I just checked it. I'm very sorry for the disturbance. So there will be some thermal noise even at room temperature. Okay, so at room temperature you are performing experiments, so that is, so you will get some ITH intensity in the detectors even when there is nothing is going, okay? For that this opaque part is required. When you already know this thermal energy is KBT, right? KBT is thermal energy. So if the temperature is low, then your ITH will be very less. Actually what you are detecting here is, as absorbance, you are detecting I 0 plus ITH. I should not have written like this. I transmitted plus I thermal. If the I thermal is less, then it is actually I0 by IT, means logarithmic of. So I'll put it like this, 10 to the power n. Okay, so it will be like this. But if I thermal is too much, then this problem will occur. So to get away from this problem, this thing is there, that when the first wheel will be in the opaque part, the second is also synchronized to be in the opaque part. So though no light will go through, and that time I thermal will get what is the ITH, and that will be deducted from there, and will actually get a proper absorbance, like what we want to get, that is I0 by IT. So once we'll detect, so and this I told you this wheel will rotate very fast. So at time t1 we will detect, suppose I0, time 2 will detect I t, and this delta t, that is t1 minus t2, that is very less, as they are rotating very fast. Okay, and these are all synchronized. Then this problem of two detectors or different sensitivity, those problem can be avoided. I hope, and I hope this is clear, right? Is it clear?
Yes, sir.
Okay. If it is not clear, you can always ask me in the discussion forum. And now I will discuss one more thing, that is the quantum yield, right? That has also been discussed. So quantum yield. Also write it phi f. In class, it is being taught that phi of a sample is actually. So I will write it in some other fashion. The number of photons emitted by total number of photons absorbed. Okay. So this is what is actually the quantum yield, and generally it is actually almost you can say it is intensity, or the sum of the intensity I emitted by I absorbed, what is being taught in the class. And from here I think it was shown that you can deduce that I absorbed can be replaced at I0 1 minus 10 to the power minus a. Do you need a quick recapitulation, or you already know this thing? Avantika? How we are coming from I emission by I absorb to this. I hope this is already in lecture, so I will not discuss this much more. And as we are saying, this is for sample, so I will write sample, I emission sample, and I0 is the incident light and absorbance of the sample. And actually what has been taught actually that quantum yield can be reported using a standard quantum yield standard, or which is a common dye like coumarin 153 or rhodamine 6G or fluoroscene. The fluoroscene. Actually, these all have different. Actually, to get a proper standard, what you need. Suppose this is your absorbance spectra of your sample, and this is suppose lambda nanometer. Suppose this is your absorbance spectra. So you need to choose a fluorescence standard which have a proper overlap with your so this is for your sample, suppose sample, and your reference or the standard should also, suppose this is for your standard, they should also have an overlap in the absorbance region. So suppose you will excite your sample here, and you also have to excite your reference at that particular lambda. I think it has been taught. You have for so let me write it once for the reference of the sorry. So this is I emission for the reference. So what I am discussing this because there is a problem in assignment 1 for this. I think you can do that from here. Standard or reference, what I am trying to say. So your lambda of excitation should be same for your sample and the standard. So that is why you need this your standard should have an overlap with your sample. Your sample could be different, so that is why you have a multiple library of fluorescence standard available. Why they are called quantum field standard? Because if you vary the lambda excitation, the quantum field of that sample is not actually going to change much. To be precise, if I say there will be some change, but it will not be a huge change. That is why they are called quantum field standard, which is not true for all the fluorescent molecules. That is why not all the fluorescent molecules are fluorescent standard. Okay. So the question in the assignment, you have to solve it like that. So I have changed this thing, reference standard, sample here, but you can see that I0 will be the same because we are doing in an identical condition. Okay. So that is why from here, so your assignment 1, I think you phi if R is already given and these all are given, only you need to get the I0 from there and put that here, or you can just do a reference something like this, a ratio. You will get I emission is 1 minus 10 to the power minus A of sample into 1 minus 10 to the power A of reference and different I of your I emission or your reference. You are going to see in future, future means there are some terms also important to calculate quantum fields, which was not discussed in the course because it is not a fluorescence spectroscopy course, to be honest. But let me give you that flavor because we are discussing here. Actually, a solvent will also play a part here. So that is why refractive index of your sample, suppose your sample is in methanol, okay, and your reference is in water. So then the refractive index of your sample is also going to be a part. So these are all square. Actually, I should not write eta, it should be n, right? Refractive index is n. The viscosity is eta. So n square of that of the sample. This is also going to come. If you look further, if you study fluorescence, you will see this, that quantum will there is this parameter, solvent parameters is also there. But the problem given in the assignment 1, you will need only this formula. Okay. You can. I hope you can do that. Okay, then okay. Let me see how much time do we have left. I will go right there. Okay, we have 40 another 40 minutes. So I think the emission instrumentation, you don't really need an discussion, but still let me give you some idea. Emission instrumentation, what I am trying to, I will quickly draw that thing and I will then discuss. So there is one monochromator unit is there, which is known as excitation monochromator. I will not write much. Here will be your sample, right? This is your sample. Here you don't need any reference, right? Any means any blank solution you don't require, because your the fluorescence will only come from your fluorescence sample or the fluorophores. The solvent itself is not emitting. At 90 degree means to that of the source, your detector and emission monochromator is there. Emission monochromator and your detector will be there, which is generally a PMT detector or something else. So for a emission measurement, you suppose this is lambda nanometer and this is increasing here, and suppose this is your intensity, fluorescence intensity. So what you are actually doing from the for absorbance, you have seen a 180 degree instrumentation, right, or the pathway. But for fluorescence, why we are choosing a 90-degree setup? Because we don't want, we want to avoid this upcoming incident light. The incident light will go here, and your fluorescence is actually is going to all over the direction. It does a directionless thing, right? One part of which is collected from this 90-degree measurement. So to avoid the incident light from the laser, a laser source, actually a xenon lamp is used as a source in fluorescence fluorimeters. So this is what I was saying. So what actually you do, you first measure an absorbance spectra, which is like this. Suppose your absorbance is like that and your lambda is this. Suppose this is your absorbance spectra, and from here you are getting an lambda absorbance max. You can choose any wavelength here to excite your sample, but for generally what we do, we take the lambda absorbance max and we excite it at that particular wavelength. Suppose you are choosing from the excitation monochromator, you are fixing lambda absorbance max. Suppose we are choosing 350 nanometer, and you will vary your emission monochromator. There is some range known as 350 plus 10 nanometer. So these are just information. So if you are not getting it, please let me know. 10 nanometer. This is one range. Means lambda excitation plus 10 to 2 lambda excitation minus 10. So there is why we are taking plus 10, to avoid any scattering that is coming from the first order peak, known as the first order peak. We will go ahead plus 10 nanometer, and to avoid the second order peak, we will decrease that 2 lambda x. There is another second order peak will come. To avoid that, we will take our spectra in between this range. So suppose you will get something like this, your fluorescent intensity. So you can have 2 peaks or multiple peaks, a single peak also, or multiple peaks as well. For anthracene, we will get multiple peaks. So what I am trying to say here, suppose you are fixing your lambda excitation monochromator and you are varying your emission monochromator lambda by lambda. So at each lambda, your intensity will be detected and your emission spectra will be collected. Okay, is up to this part, is it clear? And this was being discussed in the week 1, lecture 1. I hope these are all means you already understand this part, right? So I will go to week 2, lecture 2, week 1. If you have any doubt, you can tell me. Else I am going to week 1, lecture 2, where it has been discussed about the monochromators. So till now, do you have any doubt?
No, sir.
Okay, thank you for your response. So for the monochromator part, I think Sir has already shown in the lecture. So I will not draw in explicitly, but the important part is there is a grating, right? Grating where that lambda, n lambda is equal to 2d sine theta. That Bragg's law is an important factor here to get our to separate the white light into multiple. Suppose white light to its different component, different component will be different lambda after that grating, right? Something like this. You will get that. And there are 2 slits, means I am just discussing the components here, I will not drawing the thing. There will be 2 slits, one is entrance and the entrance and exit slit, right? And there are some lenses, right, to focus or converging lenses, and there are some mirrors. So how do we, so in the previous part, so this monochromator is true for excitation monochromator as well as emission monochromator. You understand? So I told you that we scan the emission, during emission we scan the emission monochromator. So that scanning means scanning in monochromator is actually means that we are changing the tilt of the grading, not the other parts. We are not going to rotate the mirrors or anything. Yeah, we can change the slit, but that is a different issue. But we are not rotating the lenses or mirrors. Okay, so that will give us. That is how we will get. Suppose that is what the scanning means. Means we are changing the grating so that different wavelength will come. So that is one thing. And in lecture 3, so actually this will be very quick. So in lecture 3, it was discussed about the resolution of a spectrum. Resolution, then detectors or signal to noise ratio, something like that. So do you have any doubt regarding these resolution, detectors or signal to noise ratio? So can any of you tell me that what does resolution means? So the resolution means, Avantika, what does the resolution means? Is it a better resolved spectra, or this is a better resolved spectra? What do you think? The scale is same. Suppose this is lambda 1, lambda 2. What do you think? What is a better resolved spectra here? Can anyone tell me?
The second one.
Second
Second one is the better result.
better result. Why? But see that both the wavelengths of both the spectra is actually overlapping. Means you can't really, you have a overlap between lambda 1 and lambda 2. So, but if you see, you can see lambda 1 and lambda 2 properly in this picture, picture 1 and picture 2. Actually, the resolution is better in this case. Means the resolution means you can differentiate 2 points or here for the 2 wavelengths clearly. So in which case do you think the wavelengths are much clearer? Is it not the first case where the resolution is good?
Yes, this first.
Yeah, I think there is some message in the chat box. Let me see. Is it there? Some message? I forgot how to check that. I don't think so. Okay, sorry. Let us go back to our study. Yeah. So the first picture is the more tells us about the higher resolution. So to get a resolution, what Sir I think showed you that lambda 1 is equals to, suppose we are only considering n is equal to 1, that is the first order thing, that is 2d sine theta 1 for lambda 1. For a lambda 2 you need a different tilt angle, right? That is here, that is suppose sine theta 2, what we are discussing here in the monochromator. So suppose delta lambda is the difference between two lambda 1 minus lambda 2, that will give you 2d lambda sine theta. What does lambda sine theta is? Means it is not practically lambda delta sine theta, it is actually sine theta 1 minus sine theta. Okay, so you will see that delta lambda by delta sine theta is actually 2d, right? So higher resolution means smaller delta lambda. Okay, so means you can so if the resolution is high, means you can differentiate between two lambda to close lambda 1 and lambda 2. So delta lambda means if delta lambda is smaller, then your resolution is high, and to get delta lambda high, you need d, that is the distance between the grating lines, that you need to be small also. Okay, so smaller, but you can't really play with theta 1 and theta 2, right? Because at a particular theta 1 you get lambda 1, and a particular theta 2 you get lambda 2. So you can't really play with that, but your d has to be small. If you want your delta lambda to be small, your d has to be small. The smaller the d, means the more the lines. So the distance between two lines are less, means the more lines will be there. Smaller the d, smaller the delta lambda, higher the resolution. Okay, and what is the another factor that can, so this is one factor behind the resolution. Another factor is the slit width. So as the picture, suppose this is a slit, let me dot two slits. So this is a second picture and this is a first picture. In the first picture, the slit width is less. In the second picture, the slit width is more. So what we have seen, suppose the lambda 1 was coming like this. Lambda 1. Let me draw this also. Same tilt. Lambda 1 for red. Let me take another color for the lambda 2. Suppose your lambda 2 was coming like this. Lambda 2. So what do you think? In which case you can get higher resolution? Smaller slit width or higher slit width? So the whole point, smaller the slit width. Yes, you are correct. So the main point is we need to differentiate between lambda 1 and lambda 2. So if we decrease the slit, then only lambda 1 can pass through, and when we change the slit in such a way that lambda 2 will then pass through the slit, lambda 1 will be blocked. So yeah, you are correct. Let me go back to my red pen. Smaller slit width is also a smaller slit width, right? Yeah. So these two things are required for a better resolution. Now I'll not discuss how much the thing was discussed, but the type of detector that has been discussed, I will not write it here, I will just speak of them. So you have seen of single photon detector and array detector, right? It has been taught. The array detector will, for array detectors, you can actually have a long higher slit width, and suppose your array detector means there are multiple detection points are here. So lambda 1 will fall into 1, lambda 2 will be fall into 1. So your resolution doesn't really, or your whole picture will come at a single point. But if you, so you don't really need scanning much scanning in case of array detectors. But if you have a SPD, let me write it like the single photon detector, and for this array detector AD, array detector. So you can see that for SPD you need a scanning, but for array detector you don't really need that much scanning. And there are different kind of detectors being discussed. So I will not go into that because it will be repetitive. So let me also talk about signal to noise ratio. So can anyone tell me why signal to noise ratio is important, or what does it mean, signal to noise ratio? So noise means suppose thermal noise or any other kind of noise. It is actually denoted by S by N, and it is also shown from Poissonian equation that noise is actually a root over of your signal. So I think it has been already shown, if your signal to noise ratio is high, then you get a good data or good spectra. So what I am trying to say, what is the difference? Suppose this is your fluorescence intensity and this is your lambda. You get something this high signal to noise, so your noise is less. But suppose you have a very small signal is coming, then you could observe. Oh, wait, sorry. You can get a noisy spectra like this. Signal is less, and there is high noise. So for the same sample, what do you prefer? A good signal to noise ratio, a good spectra, or a bad spectra? Obviously the better one, right? So for that you need a high signal to noise ratio. I hope this part is also clear. This was till now was discussed in the lecture 3. Can I go to week 1 lecture 4 that will deal with the time domain spectroscopy or time domain spectroscopy. So do you have any doubt till now? I guess no. So
Actually,
okay, yeah, Avantika, yes,
actually, in this signal to noise ratio,
yes,
two columns in the for decreasing temperature, there were
yeah,
two facts that were mentioned.
yeah.
One Peltier effect and other feedback effect. Can
One
you
one regarding,
tell us something?
can
One is
you,
Peltier effect and other one is the feedback effect.
yeah.
Yeah, can you tell us something about this feedback effect?
CVEC effect, rightly I can't really remember. I will share some information in the discussion forum. Are you a participant of that discussion forum? Did you join that discussion forum?
No, no, not.
So what you can do that you let me show you how to. So this is an perfect opportunity for me to show you that thing. This is a very useful thing for you guys. Please check that. You can see my screen, right? So this is going to be your so this is the website, or this is the screen you get when you enter the course, right? Something like this, is it?
Yes,
No?
yes, yes.
Yes, right? So you can always go to ask a question here. Okay, I have just clicked that link, and you can go to discussion forum. So this is a discussion forum for this molecular spectroscopy course. Means where if you so how can you join? So I think I have already joined. That is why my Google ID is also showing that, that is already shown. When you will try to write that, you will be asked to give your email ID or the Gmail ID you are taking your enrollment ID, means the Google ID you have used, and you can join and you can ask your question, or even if you are not asking question, you will suppose how to start a conversation, a new conversation you will go. For you it will not be Orko Provo, it will be Avantika. You can write your subject here, and you can suppose post your doubt here, like tell me, give me some reference related to I don't really remember the spelling, some Seebeck effect, or okay, I am not sure what is the spelling. Do you know? Are you
SEE
S double E
BAC.
B A C or E C?
SEE BAC.
Oh, sorry.
BACK.
Seebeck effect. You can write it like that, and you can post your message, I guess. Acha, you can only post your message when you have a subject. So you can copy that thing, write doubt regarding civic. Then you can post your message. So we'll also get it, and whoever are the participant of the discussion forum, they will get it when we will reply it back to you or to all. So it will be there for all to see. Okay. So I will try to upload some documents or text related to the Seebeck effect. If you means I don't really remember that part right now. So I will also read that part, and if you still have some doubt, I will discuss it in the beginning of the next session. Okay. Will it be fine?
Yes, sir.
Okay, thank you. And please don't call me sir. I am a student, just a PhD student. Don't worry. I know it is difficult for me also that to not call the TAs sir, but we are not really sir. We have not earned that status yet. Why did I keep my pen? Wait, where is the pen? Give me one minute. Sorry for this thing. Where's the pen? Oh, I got it. So actually I am conducting this session from my lab only, and so I had to choose a very small place where no one is there, no one can disturb us. Okay, so what I was trying to other than the Seebeck effect, do you have any other doubts on there?
No.
Okay, till now you don't have any other doubts. Now let us talk about time domain spectroscopy. So till now what we are seeing, nu or lambda anything, so or with suppose this is intensity or absorbance something in as a function of frequency. Let us not write lambda right now. So these are all interconvertible, as you know, right? So suppose let us think about the ideal condition where you are getting a spectra. It should be the ideal condition where I am saying that so you will get for atomic spectra, you know, the line spectra you should get, right? So it will be suppose nu 1. Okay, so ideally you should get something like this. And if I convert it to time domain, what does it mean by we are doing? Suppose this is time axis right now, and suppose this is another function which is a function of time. So suppose a cosine or a sine function. Let us take cosine function. You can take sine function as well as, there is no problem. We just have to take the frequency. How does a normal cosine wave looks like? Suppose So this is a general thing, right? Nu t, suppose this is amplitude A, this nu is the frequency, and this is the time, right? So suppose, so this will be, if we transfer this here, so we'll get something nu 1, suppose nu 1, so that will be the frequency of this wave, okay, and it is going, it will go. So if you, from here you will get only one frequency, that is nu 1, and that if you see that thing in the this is in frequency domain, and this is in the time domain. But as I told you earlier, that this is not really an normal thing. This is an ideal situation here. So you really get a spectra like this, band like spectra. So if you need to transform it from frequency to time domain or time domain to frequency domain, actually you will get a spectra like this. Are you getting my point? What I am trying to, I think this has been drawn well in the class. Somewhere you will get some, so this is not at par the scale, but something like this. Somewhere you will get some, where you will get some constructive interference, there you will get something like this, and where you will get, means this is a constructive of, suppose A cos nu 1 t plus B cos nu 2 t. Okay, even you can have sine functions. Okay, nu 3 plus D sine nu 4 t, and it will go like this. You can have so as you can see here are multiple news are present, right? Multiple news are present. So for frequency domain measurements, what you had to do, you need to scan all over this nu or lambda, right, to get this spectra. So it is time taking. At each point it will take the intensity or that absorbance to get this. But this time domain spectra, this thing you will get at a one go. At one go you will record this. So this is one of the advantage of time domain spectroscopy. And from here we can actually, there is some method known as Fourier transformation, which we will not discuss in this discussion forum or in the class as well as, because that is not a part of this discussion. But I can share some text of that in the discussion forum if you wish to study that. So we can interconvert this from frequency domain to time domain and time domain to frequency domain using a Fourier transformation, that is known as. And suppose this spectra in time domain is a collective of or a summation of this many frequencies and these many waves. From there, at a one go you will record this. Okay, at a one go you will record this, and after Fourier transformation you will get a spectra like this. Means that will have all the data or all the signatures of this nu 1, nu 2, nu 3, nu 4. I hope I am clear. Is there any doubt in this part?
No.
Okay, thank you. So can you tell me the advantages? One I told you. What are the other advantages you can think of? What about resolution? Resolution will be better in time domain spectroscopy or frequency domain spectroscopy. What do you think? Actually, resolution will be better in time domain spectroscopy. As you can see, this in this is actually called a interferogram or something like that, where you get the this kind of spectra. So so you can get it from two frequencies or two waves, or you can break it into multiple, means more than two frequencies or more than that waves, right? So the resolution will be, so you will get much many frequencies or much more points. But here here the resolution, yes, you can go, you can have some better resolutions here as well as in centimeter inverse. Now the spectroscopy has gone to so far that you can, so very small resolution means high resolution you will get from the frequency domain as well as, but anyway the resolution of the time domain will be much more. And as you are getting this data at one go, that means you are collecting much more signal at one go, right? So your signal to noise ratio will also be better in time domain, and that is why you will get a better spectra when you do a Fourier transformation of that. But generally in fluorometer or in UV absorption, we generally do frequency domain measurements, means where the axis is new generally. And in case of I think you have heard of FTIR, infrared spectroscopy, and NMR, nuclear magnetic resonance spectroscopy. There they use these time domains. They collect the time in time domain, and then they do Fourier transformation to get spectra from them. Okay. I think one last lecture is remain, and we have still 10 minutes of time, where actually it has been discussed this limitation of a interferogram or a oscilloscope. So actually there has been actually this whatever the live lectures you actually the lectures you are seeing, actually this has been taught a few years back. As you can see, it has been recorded from a classroom. So sir has made one minor mistake there. So I will just take this opportunity to I think you all must have that doubt. So I will show it, but it will not a very big mistake. So let me tell you that. First I will quickly draw the interferometer, Michelson interferometer. Actually this is this Michelson interferometer we are using so that we can do a frequency modulation. I will come to this part. I know there might be some lack in understanding in this part, but I will try to clear it. See, I also am not an expert of Fourier transformation of this kind of thing, so I also may have some doubt here. So, but I will try to clear that. So this is the source. This is a high reflective mirror, as you have been taught, right, in the class. There will be a beam splitter will be kept like this, 50-50 beam splitter, BES, and it will go to some, and there it will go from here to here, some reflected light will go here, and there will be a stationary mirror. Okay, so stationary M mirror, and there will be a mirror which can what I can say, movable mirror. So it will hit here and it will come back the same path, same as here, after falling to the mirror, and then it will again come here and it will fall into again some parabolic mirrors. So these are parabolic mirrors where actually no light will be lost and it will come to the detector. Okay, and at the focus of the parabolic mirror, the detector is being kept. This is detector and this is source. So the actually what Sir showed actually, actually let me tell you. So this is actually the interferometry, actually a thing of wave, means constructive depends, means it is based on constructive and destructive interference pattern, right? Interference pattern. So actually when the difference between two lambdas, suppose we are changing the, so this mirror is stationary and we are moving this mirror. So let me give you the correct thing. So if we move a mirror by lambda by 4, okay, so so this is actually your delta, or you can say this is mirror movement. Then your optical path difference, that is OPD, let us acronym this OPD, optical path difference, actually double of that 2 delta, right? The path length, so light will go here and it will come here. So if it is lambda by 4, then your OPD, so delta and OPD, let me write it like that. So it is lambda by 4, then your OPD is actually lambda by 2. And if your delta is lambda by 2, means we are moving, so lambda means lambda is in nanometer, right? So we are moving this mirror very small distance or something like that. So suppose it is moved to lambda, so if the mirror gap is lambda by 2, then you will get a OPD of lambda, and you will see the constructive, for constructive interference we will need a integer number n lambda difference as a OPD for constructive interference, and for a destructive interference you will need n plus half lambda. Okay, n could be 0, 1, 2, anything, whole number, huh? Here also n could be 0, 1, 2, anything. For a destructive interference you need a n plus half lambda, and this is the case. So actually what Sir has shown, if as a delta, if you have to show this, suppose p of t, or suppose something like that. So suppose when the delta is actually 0, then it will fall over each, huh? But at this gap, what I am trying to say, suppose this is delta, so delta, when delta is lambda by 4, lambda by 2, suppose 3 lambda by 4, is it 3 lambda by 4, 3 lambda by 3 lambda by 4, then lambda, okay. So constructive, so for constructive, and there could be in between, right? Lambda by 4 to lambda by 2, there are some in between part. So for lambda at 0, means when there is no path difference, means this is, we are changing the delta, so this is here, the delta is 0. So when delta is 0, there is no path difference, so this is the condition here, 0 lambda, so we will get a constructive interference and we will get some data here. At lambda by 4, what I am trying to say, the optical path difference will be 2 lambda, that is delta by 2, lambda by 2, and that will give us an negative or destructive interference, and it will actually will not get any signal from it. Okay, and again in lambda by 2, what is going to happen? When the delta is lambda by 2, then your OPD is becoming lambda, that is 1 lambda, we will get a constructive thing, and we will again get some point here, right? And this will, at 3 lambda by 4, we will have destructive interference, at lambda we will again have constructive interference. So it will, and there will be in between points, so this is not a continuous line, it will go like this. So are you getting this point? So actually, why this Michelson interferometer was important, I think we are already hit our time, but I will take 5 more minutes to complete this. So actually, the frequency of light is very high. I hope you will be agreeing with this, me, right? To get an idea, see this, we all know, right? Energy is hc by lambda. I use this formula to get to take the relationship between c by lambda to be valid. So as you can see, if your c for light, c is very high, right? 3 into 10 to the power 8 meter per second. So your frequency is also very high. So we don't have such instrument to operate at that speed. So we'll take frequency of this mirror, movement of this. Actually, if you see for a constructive, what Sir has already shown in the lecture, you can always refer to that. For a constructive interference, you will see that it will suppose it will take time t, tau time, for a mirror movement of lambda by 2, right? Because you want, so your for a constructive interference of this, we need a delta of lambda 2, means your mirror have to be moved lambda by 2 unit. Okay, and then your optical path difference will be lambda for a constructive interference. Suppose this time it will take a tau time. So the frequency will be frequency of the signal or this mirror movement is 1 by tau, and it is also, we will also know the this is the velocity of the mirror movement. So from here we know that velocity into time tau, it will give us lambda by 2. So from here we know that Vm, tau is actually lambda by 2 Vm, and this will give us the frequency of the signal. This is not the frequency of light. Frequency of the signal will give us, it will be 2 Vm by lambda, and this lambda is also related to the light, right? And from here we will get 2 Vm into, suppose nu bar, I am writing like this, or 2 Vm into nu by c, frequency of light. So you can see that our instrument, what is in our hand, that the movable speed of the movable mirror or this frequency, that is actually related to the frequency of, means we can relate it to the frequency of light, and this is frequency of your signal. Actually we can't really have this frequency in our instrument, but this, from there we can anyway go to the new. So there is an assignment in the week 1, I guess you have seen this or you can see that. So what you need to do that you need to put up the values. I think you will need this new bar, this value, and you when the answer will be released, you can see what the values you are getting. Okay. So the discussion behind this lecture 5 is all that We will use this interferogram so that, because we don't have that, we can't really operate our instrument at the frequency of the light, so we'll operate it in our hand, that is f, that frequency, and we will convert it to nu in the latter half. Okay, so just the scaling thing, we are just scaling it down to a lower thing. This is all in time domain thing, right? So because that is why I am taking this y as a p of time, function of time. Is it clear till now, or there is some doubt? We can anyway come back later and discuss these things. So what do you think? Is it clear? Is it a effective discussion?
Yes, sir, it's clear.
So even if you have some doubt, anyway you post it in the, so we'll stop it here. Let me go back to the meet and stop my presenting. Stop presenting. I hope Saptagiri and Keshav also learned something, or I hope it is helpful to you guys. I hope. How was it? Means is it previous time what was there, that we were doing a 1 hour session, this thing. So we will only discuss the questions, assignment questions, but not really much of the doubts in the lectures were being cleared. So PMRF has now actually told us that we should conduct a session of 2 hours, so that we can elaborate all the things. So is it a good 2 hour discussion, you think, or I will need your feedback, so that next time I will do something else if you want some more problems to be solved. That I will also some numerical problems I will find out, because till now not much spectroscopy or those numerical problem has been taught. When it will be taught, I will take some numerical problems I will take, and we will solve that here also. But was it useful, or what do you think we can improve for this session? Avantika, Keshav, Saptagiri, please, I will need your feedback. What do you think? What can be more can be done? Keshav has written. Thank you very much. I hope it is helpful, and I will update few things, means numerical problems, as I have said, we'll do it much more things, and we'll try to limit the lecture, whatever is the lecture part is already discussed. I will add something like the double beam spectrophotometer. You didn't know about the wheel thing, so I will add something like that, what sir has not covered because of time permission. I'll add those point. I'm researching on fluorescence spectroscopy. So these parts are somewhat clear to me. I will, and we know actually I'm in my third year. So I'll try to discuss those things as well as. So okay, I hope to see you guys in the next session as well as. Thank you for joining, and you will find this thing recording video will be uploaded to YouTube, and this notes, whatever presentation I have given, the slides and notes will be given. And Avantika, I will share the CVEC effect thing in the discussion forum. Please join there, and Keshav, Saptagiri, please, you guys also please join there in the discussion forum as I have shown. Okay, then you guys can leave, and please come in the next session so that we can have a fruitful discussion. Thank you for joining.
Thank you, sir.
You too, Keshav. Have a good day.